Hi everybody, Patrick here from EngineeringShock.com and ElectronicLessons.com. Today we're going to talk about a decade counter. We're going to talk about the 74LS93. Now this is the fifth electronic block tutorial video that I'll be of several that I'll be making for our electronics learning board. The electronics learning board is on pre-order right now and a link can be found below. The goal is to teach you all of the different electronic blocks so that you understand how they're working, so that you can plug them all together and make all sorts of different experiments on our learning board. Anyhow, before we actually get into the hardware, we have to talk a little bit about binary. Now, I'm also going to link below a better tutorial that I have on binary that I made many years ago. But this is just going to be a quick recap on that. When we talk about binary, we're talking about zeros and ones. But electronically, at least for the circuitry we'll be using, it'll be essentially 0 and 5 volts. With 0 volts being 0 and 5 volts being a 1. So we'll get to that in a minute. That'll make more sense in a minute. But what we have here is a table. This is our decimal value, 0 to 10. I'll get to this in a minute. It says A equals 10. I'll get to that in a minute. We've got 4 bits, A, B, C, and D. And they have different values. But first of all, A is our least significant bit because it has the least amount of binary weight. And our leftmost bit, our always leftmost bit, is the most significant bit. In this case, because there's only 4 bits, the bit D is our most significant bit. The least significant bit is worth 1, 2, 4, 8, the next would be 16, the next would be 32, the next one would be 64, and so on and so on and so on. It keeps doubling. So, in order to make a truth table like this, for the least significant bit, it's always toggling, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, and so on. Our second bit is 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, and we keep doubling that. Our third bit, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, and then adding 8 zeros, 8 ones, and then there'll be 16 zeros, and 16 ones, and so on and so on. That's how you make a basic truth table to count up in binary. So, if this bit is worth 1, this bit is worth 2, this bit is worth 4, and this bit is worth 8, when we have a case where all bits are 0 volts, equaling a 0, our decimal value of this 4 bits is 0. If our A bit is 1, 5 volts, and the rest are 0, our binary weight is 1, so our output has a decimal value of 1. If the second bit is a 1, that binary has a weight of 2. Since all others are zeros, our decimal value is 2. In the case where our A and B bit are high, our 1s, 1 plus 2 is 3. In the case of when bit C is high and the rest are low, bit C has a binary weight of 4. In the case of bit A and C being high, C is 4, and A is 1, so 4 plus 1 is 5. 4 plus 2 is 6. 4 plus 2 plus 1 is 7. Our MSB is worth 8. So when the D output is high, the rest are zeros. The decimal representation is 8. 8 plus 1 is 9. 8 plus 2 is 10. But that's when we start getting into hexadecimal. We don't actually use tens. We use A's. It goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B, C, D, E, F. So that's a whole other story. The counter we're going to use can count up to essentially 15. 8 plus 4. If all are 1s, we can keep counting up. If all are high, 8 plus 4 is 12, plus 2 is 14, plus 1 is 15. So basically, our decade counter can count between 0. If we count 0 as state, all zeros as state, then we can count 16 states including 0, so 0 to 15. So what we're going to do is we're going to create this. We're going to use a 555 timer oscillator. Now, I'll link our tutorial for that below, and we're going to use that to increment our counter. And we're going to put LEDs at the outputs so that you see the representation of what this really stands for. And in our next video, what we're going to do is we're going to plug our counter circuit into a 7-segment display decoder. Now, hold on for 1 second. We'll talk about the hardware. So this is the 74LS93. It's a 14-pin chip. Left-hand side of the chip, there's a little notch to indicate where pin 1 is. Pin 1 is just below the notch. 2, 3, 4, 5, 6, 7. 8, 9, 10, 11, 12, 13, 14. So we'll talk about those pins as we go along. First of all, we're going to talk about our power supply pins. But I also touch on this. I continued on the truth table to discuss A, B, C, D, E, and F, which equates to 10, 11, 12, 13, 14, 15. 15 is F in hexadecimal. That's not really all that important. But this 1111 has a binary weight of 15. So again, we just keep toggling bit A, adding another 0 here, and then another 1, adding 2 more zeros to that, and 2 more 1s, adding 4 more zeros and 4 more 1s, and so on and so on. Anyhow, let's talk about the 74LS93. It requires 5 volts, no more. It will operate probably around 4.5 volts to 5.2 volts. You have to be very, very careful. This is a TTL chip. There's nothing fancy about it. If you don't have a well-regulated 5 volts, it will not operate correctly and you can fry it. So let's talk about the power supply pins. This is a 5-volt battery representation. Longer lead indicates positive, shorter lead negative. This is our ground reference point. VCC is our power supply reference point. In this case, is 5 volts. I'm going to make a power supply video, and when it's done, I'll place it in the information area below, along with all of the other links I've talked about. Now, pin 5 is our VCC pin. So this is a reference. So imagine a wire going from this pin, pin 5, to here. And this is upside down, but that's a ground point. Pin 10 is our ground. So imagine a wire going from here to here. Now this fits nicely in your breadboard. Again, I will be doing this myself and showing you myself plugging this into a breadboard in a few minutes. But first, we have to discuss the outputs and the clocking inputs. Now, after I'm done explaining this, before we get to the breadboard, I'm actually going to show you kind of what's going on inside here, because it's very important that you know. Counters really require a separate tutorial. This is more of a hardware tutorial, but I will get a little bit into how it's working, because you can do a lot of neat things with this chip. So let's talk about the outputs A, B, C, and D. Okay, so output A is pin 12, output B is pin 9, output C is pin 8, and output D is pin 11. So what I've done is I've taken 4 470 ohm resistors, the current limiting resistors, and 4 LEDs. Now, in case you don't know much about LEDs, there's a positive side, the anode, and a negative side, the cathode. The positive side, the anode has a long lead, and the negative lead, the cathode, has a short lead. So our long leads would be here, 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 and here, and our short leads would be here, 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 because this is the negative side of the diode, and they're all connected to ground. So these resistors basically say to the inputs, I only want a little bit of current. I'm telling you how much current I need, and that current will drive the LEDs. So this can be 300 to 600 ohms if this is on a 5-volt device like this. The outputs, I think, can source about 10 milliamps. Anyhow, I digress. Going back to it. So what I've done is I've connected A to our A LED, B to our B LED, C to our C LED, and D to our D LED. So think about these as the zeros and ones. When these LEDs are lit up, consider it a 1. And when they are not lit up, they're a 0. This is how this is a binary representation. So if A is lit up and D is lit up, D has a binary weight of 8, A has a binary weight of 1, 8 plus 1 is 9. If D and B are lit up, 2 plus 8 is 10. If D and C are lit up, 8 plus 4 is 12. If none are lit up, 0. If A is lit up and nothing else is, 1. Because A has a binary weight of 1. Remember, 1, 2, 4, 8. That is their binary weight. Haha. Okay, so now our clocking input. We need to put a square wave on a clocking input. So what we have to do is basically what we will be using. I'll be using a 555 timer. But what I'm just going to do is I'm going to say OSC for oscillator, square wave, and I'll put it on the correct pin. But there's one thing, there's 2 clock inputs. It's in here there's essentially 4 different flip-flops, four different counters, four different circuits that dictate outputs A, B, C, and D, and they work together. And I'll show you how that all works in a minute, but you have to understand that the first flip-flop is actually, imagine it as just one fragment of this entire thing. The output A, is actually, since it's right here, we actually have to feed that into a second clock input. They do this because A is always toggling. Every time there's a pulse on the clock input, A toggles. This will make a bit more sense in a second. I realize I'm rambling a little bit. Let me actually set up the clock input just so you can see what's happening. Our clock in 1 pin is pin 14, top left pin. Every time there's a pulse, as you can see I've created little pulses here, the counter will increment. It will count up 1. So if it was 0, it gets a full pulse, enters pin 14, then it'll increment to 1. Then another pulse, it'll increment to 2. Anyway, we'll see that in operation in just a few minutes. But that is where you feed your pulses, your clocking pulse. The output of the first flip-flop internally, which is output A, binary weight of 1, we have to connect that to a clock in 2 port. This will become more apparent when I erase all this and show you what's going on in here. So now there's just 2 more pins that we have to worry about. There's RO1 and RO2, pins 2 and 3. They're called RO1, RO2 in the datasheet. I'm going to call them AND1 and AND2 because AND1 and 2 have to both be high for the counter to reset. Now I'm going to show you a really neat function in a second. If I want for the device to reset at 10, what I have to do is I have to connect these 2 pins to D and B. So it would count up to 9, and the second both of those lines go high, the system resets back to 0. So basically, just make a connection from here to here, here to here. Now, if I wanted for the system to reset at a value of 4, what I have to do is connect both of them together and connect them to C. So it'll count 1, 2, 3, and the instant it counts to 4, the system resets. If we had this hooked up to a 7-segment display, you wouldn't even see 4, because the instant it hits 4, it resets. So as soon as this line goes high, if I wanted for it to reset at 8, what do you think I'm going to set it to? I'm going to connect this to D. I know I'm making too many examples here, but I really want you to understand this concept. You have the option of using both or one. Simple ones, like having it reset at 1, 2, 4, and 8, you just connect them together and connect it to 1, 2, 4, or 8. Sorry, right. Actually connected right at the ports before the resistors. But if I wanted to connect it, if I wanted for it to reset at 6, binary weight of 2, binary weight of 4. As soon as it hits 6, system resets back to 0. So 1, 2, 3, 4, 5, reset. 1, 2, 3, 4, 5, reset. 1, 2, 3, 4, 5, reset. Hopefully that makes sense. I'm quickly going to draw up basically what's going on inside here. It's really not that complicated, and I truly hope that you won't have trouble understanding it. Okay, don't be alarmed. This is not as complicated as it looks. I think you're really going to get something great out of this. So flip-flop 1, 2, 3, 4. Each of them is responsible for outputs, for different outputs. A, B, C, and D. This is our clock in at pin 14. I've got the pin outs for each of them. This is our AND. So it's actually NAND, but this is basically just to tell you basically how it's working. When the output goes high, all of the flip-flops reset. And that's pin 2 and 3, RO1 and RO2. Now this is our clock 2 pin. As you'll notice, by default, inside the chip, output B is connected to clock in for FF3, and output C is connected to the input clock of FF4. These are inverted clock inputs. So basically what it's saying is, an operation will trigger on the falling edge, not the rising edge, the falling edge. So we'll get to that in a minute here. What we have to do is we actually have to make a manual connection between clock 2 and output A, as talked about in the previous schematic. So clock 2 is pin 1. Sorry about that. Clock 1 is pin 14. So now all of the flip-flops are cascaded. We've got output A connected to clock 2, clock of our internal flip-flop 2, B to clock 3, and C to clock 4. Hopefully that makes sense. Whenever this line goes high, they all reset back to 0 state. So I've created a quick diagram here. This is our clock, and these are 5-volt pulses, and these are A output, B, and C and D output. So after our first pulse on the falling edge, the output on the A output will go high. After the next pulse on the falling edge, it will toggle low. And when that toggles low, think of it, this is right here. When that toggles low, that triggers our second flip-flop, which is responsible for our B output. And the B output will toggle high. So on our third clock pulse, that will toggle A high again. And on our fourth clock pulse, it will toggle A low again for the second time. So it will act to toggle B down. So remember, all of these are reacting on falling edges, not rising edges. So on the fourth clock pulse, because A and B, the falling edge of A triggers a falling edge on B, which triggers our first activity on C, which brings the line high, 5 to 5 volts. And it will stay at 5 volts until it receives another falling edge, which is right here. And that falling edge triggers flip-flop 4 to go high, and so on. So if you look at this logic, our clock outputs are A to D, sorry. So when only A is on, we have a binary weight of 1. When only 2 is on, as you can see right here, only output 2 is on, which has a binary weight of 2, that is 2. When B and A are on, that's a binary value of 2 plus 1 is 3. When output C is on, which has a binary weight of 4, and only that line is on, we have a binary value, a decimal value of 4. When C plus A, 4 plus 1 is on, 5. When C plus B, 4 plus 2 is 6. C plus B plus A is 4 plus 3 plus 2 equals 7. And then finally, if only 8 is on, that's a binary weight of 8. So I realize that that's a little bit confusing. I'm going to say this one more time just to show you. Falling edge. Look how these are cascaded. This affects this. This affects this. This affects this. So A affects B on a falling edge. B affects C on a falling edge. And C affects D, toggles D on a falling edge. Every falling edge, the following flip-flop will toggle from high to low, low to high. So hopefully that makes sense. Regardless of whether or not you've got a great grasp of this, I think you'll really benefit from the breadboard experiment that we're about to do. Again, we'll have a 555 timer clocking it, and we will see these LEDs light up in a binary sequence counting from 0 to 15. What I've got right here is a 555 timer pulsing at about 0.5 Hertz. So it pulses once every 2 seconds, roughly, very roughly. I haven't hooked up my chip yet, but here are my power rails. I've got 5 volts coming in. I will power it on right now just to show you the oscillator. When the LED turns off, that's when it clocks in operation. Falling edge. Trigger. Trigger. But we haven't hooked up our circuit yet. So what we're going to do is, first of all, let's connect our VCC and our ground. Remember, VCC was pin 5, and ground was pin 10. So let's connect that. So I've taken a red wire, connected to pin 5, and connected to my power rail here, and a black wire on pin 10 to indicate ground, and connected it to my negative supply, my negative DC supply. I'm using a wall transformer right now, but I'm going to make a power supply video soon that tells you how to regulate, say, 7 to 9 volts down to a steady 5 volt that's safe for these chips. Anyhow, now what I want to do is I want to set up my LEDs. So I'm going to get some 470 ohm resistors and some LEDs. So I've placed my LEDs. The negative is the shorter pins to ground, and there are my series resistors, current limiting resistors, and what I've done is I've connected the A output to the rightmost resistor, B to the second from the right, C to the third from the right, and D to the resistor on the left. So what's going to happen is, imagine our LED is our output A, B, C, and D, worth 1, 2, 4, 8. And so what we have to do next is simply connect output A to clock 2, as we discussed in the previous table. So what I'm going to do is clock 2 is pin 1, and I'm going to connect that to the A input on pin 12. So now we're just about ready to go. But we haven't talked about our AND inputs, our R01 and R02, which are pins 2 and 3. Because I want it to count successfully from 0 to 15, then reset back to 0 on its own, what we have to do is merely take a wire and ground either pin. If you leave them unconnected, it's called floating, and it'll actually assume 5 volts, so the device will not operate if you leave them unconnected or connected to 5 volts. I want nothing to reset this. I want it to reset on its own at 15. So right now, if I'm lucky, if I haven't missed anything, I should power it on and it should start to count. Okay, so my LED's flashing. Why am I getting no activity here? Because I'm an idiot. I forgot to connect the oscillator output to the clock in input, which is on pin 14. So, there we go. 15. 1. Sorry, 0. 1. 2. 2 plus 1 is 3. Binary weight of 4. Output C. 4 plus 1 is 5. 4 plus 2 is 6. 4 plus 2 plus 1 is 7. 8. 8 plus 1 is 9. 8 plus 2 is 10. 8 plus 2 plus 1 is 11. 8 plus 4 is 12. 8 plus 4 plus 1 is 13. 8 plus 4 plus 2 is 14. And 15. Sorry, to keep up. But notice that every time the LED goes out, that's when it triggers. It's triggering on the falling edge of the square wave that's being fed into it. And every time one of these LEDs turns off, it toggles the state of the next LED. So I hope that makes sense. I realize that this was a very jumbled video, but counters are very, very important. They teach you flip-flops and counters over and over and over in school. At least they should, because they are an amazing part of the hardware world. Flip-flops we'll talk about another day. But you see, this is how systems talk to each other, zeros and ones. And these are just representations of how it all fits together. So I hope it makes sense. 8. 8 plus 1, 9. 8 plus 2 is 10. 8 plus 2 plus 1 is 11. I hope you get the picture. Go back and watch it again. What we're going to do with this circuit is look at output A. It's always toggling. On. Off. Toggles on, toggles off. So we can use that output to toggle a whole bunch of stuff. And that's what we're going to use that for on the board. But this counter, on the learning board, we are going to create, this is the learning board, by the way, if you haven't seen the video already. What this will do is we'll have a 555 timer clocking a 74LS93 clock, binary decade counter, and that will be fed into a 7-segment display decoder, which we'll talk about next, and that will actually drive and increment the 7-segment display. So the idea is you learn the blocks. Listed below are the other videos. 555 timer clocks the 74LS93, which the outputs are fed into a decoder, which drive the 7-segment display. This is how it works. This is how the blocks work. For those of you who are still watching and haven't gotten tired of me rambling on, thank you. I appreciate it, and I hope you have a great day.